second plenary talk will be delivered by Dr. Royston. Royston is from industry, has been in industry for 30 plus years. Royston works for one of the largest engineering simulation company, Altair, from the US. Altair is a massive company. It's smaller than ANSYS and Abacus, but at the same league. So that's the size of the business. And Royston has been senior in the company for many years. He's currently VP, Vice President of the company, in charge of global automotive sector. Because of the nature of Altair suite, they are strong in engineering simulations, and in the past few years they are moving rapidly into the AI space by acquiring a number of companies in Europe and in the US. Some of those were acquired from fintech sector, where AI has been broadly used for finance and banking purposes. So they are, I say, perhaps leading or gaining the leading position in the industry side to drive AI in engineering applications in the broadest sense. I would also say Royston is also a Swansea alumni. Royston actually started with Oleg Sinclair, which is a big name, godfather for fan element back in the early 60s. So without further taking your time, I will pass the time to Royston. Thank you, Royston, for coming here.
Thank you for your kind introduction, and it's a real privilege to be here. Thank you for inviting me. It's a real privilege. Thank you. So, yeah, I've got a talk. I don't normally talk for 45 minutes, but I'll give it a shot. So, there's not a single equation in this presentation either, so you can relax a little bit. I think the key thing is that my laser focus is on helping our clients develop product. And for me, the real key to developing product in an efficient manner is what we call computational intelligence, which I'll sort of describe, and speed. It's such a, particularly in the automotive, it's so globally competitive that speed is everything. So my perspective, as I say, is helping our clients deliver world-class product. The automotive industry, fiercely globally competitive, even more so now with new players, regionalization, competition from China, etc. So without more ado, let me just describe what I mean by computational intelligence. So Altair's vision is that computational intelligence will drive innovation for a more connected, safe, and sustainable future. So computational intelligence is this broader term for the maths and the algorithms and the IT technology that basically underpins simulation, optimization, algorithms, machine learning, decision trees, etc., etc. So this is the key, this computational intelligence. Altair, as a company, we have these three main software platforms. So you have the simulation and design, so that's our mathematical modeling. That's packed with optimization technology. For nearly 2 decades plus, we've been the leading company in basically promoting optimization technology. More recently, the acquisitions, particularly in that AI space, data analytics, obviously key, because as I'll explain later, we'll see the rise in this type of technology. And lastly, HPC. HPC is the power behind both of these technologies. As an engineer, I've never had ever in my career enough HPC. And that still continues. And if we're going to start to do more of what the industry wants us to do, then it's really critical that we also have this HPC available to us. So an unsung hero, but it's the power horse at the back that's really driving these solutions. So let me just talk about products at the moment. Maybe most of you universities, but I'll give you some insight, simple insight into products. So this is where the industry is at the moment. I talked about rapidly developing products. So what are the barriers? Well, now again, you have to create these physical prototypes as an insurance test that what you're building is correct. And here we have one of the leading CTOs, Ned Curick from a company called Stellantis, very big global car company, essentially saying that we're building far too many prototypes. I need to build less prototypes. And then another statement from Ned is basically saying, it's frustrating how heavy these cars are. These cars are very heavy. It's not good for the environment, not good for resources, and it's not good for efficiency. So if you just take these two thoughts, one is relating to the production of physical prototyping, the other is more design-driven about we need lighter vehicles. Now, Ned's out in the public. There are many statements at this point in time which basically tie into I need to develop these products quicker. I'm developing too many physical prototypes, and the attributes of these vehicles aren't where I need them to be. So as I said before, speed is king. So why is speed so important? Well, if I can't get these products out in a certain time frame, I'll start to lose market share. This isn't good, particularly in such a globally competitive market. If it's taken me 4 years, 3 years to get a product into market, that isn't good. So then I need to develop them quicker because maybe I would be able to take advantage of various technologies such as battery technology, connectivity. The technology is developing so rapidly at the moment. If you can have a faster design time, you can exploit some of these advancements. So when I really simplify this now, from a vehicle point of view, you basically have these three quantities. You have mass, you have performance. Performance can be complicated. Performance can be its crash performance, its NVH performance, various attributes associated to the vehicle, and then cost. And what you try and do throughout the whole of this development program is try and reach this balance. You've got mass targets to hit, you've got performance targets to achieve. Now and again on a vehicle program, the timeline won't change. If the timeline slips for a product launch, it's a disaster. So it very rarely slips. So what you have to start to do is compromise. So you start to compromise on mass and compromise on your performance targets, which is not what you want to do. So if speed is king, then, wait for it, innovation is the wizard. Innovation is the magic. Innovation is the computational intelligence that can make you achieve your targets quicker. And I'll just present some of these later. This is an AI-generated image. I never thought I'd see an image of King Arthur with his crown, Merlin with his hat, and a car. So yeah, it's a bit eclectic, but this was generated using OpenAI from Microsoft. So it was called the inevitable rise of computational intelligence. So what do I mean by that? I think many of us have seen this coming for decades, and now we see a major appetite at this point in time. So it's been building up. So let me just try and give you some historic perspective around this inevitable rise. So a historic personal perspective maybe. So for me, it all started with this guy here. Jen Fay mentioned him. It's Professor Oleg Zenkovich. He was the the godfather of finite elements, a very famous finite element book. He entered my life when I finished my, just as I was finishing my undergraduate degree, to persuade us all to do an MSc and a PhD. What he was talking about even then, this was in 81, and in 81, many of you weren't even born then, but there was these computer games that were coming out. Super Mario, you could play a bit of tennis, whatever. But these games were coming out. And what he was talking about then was what he wanted to create was a physics-based virtual reality. Yeah, not just cartoons, but a physical-based virtual reality. And that was then in 81 what we all aspired to do. We were on that journey. He should have called it a digital twin and he'd have made a fortune in his marketing. But so then if we move on a little bit, if you can remember what I was saying about Ned Curic, and so where simulation started was in this product validation. It was about replacing expensive testing. So if you could test it in the physical, in the virtual world, it was cheaper. The problem was it wasn't quicker. So here there's just an illustration of various fidelities of crash models that slowly through time were facilitated by the power of the computing, the power of the algorithms, became more predictive. The industry where we're at the moment, simulating complex events like crash, is fairly straightforward now. Why is it straightforward? Because the industry heavily invested in understanding all the characteristics of this type of behavior. So what we started to see, because the methods became quicker, was we started to do more and more simulation to replace physical testing. So that was me there. That's where I started, coming out of college in 84 with my PhD and with the professor. And we started along this journey. I think where the industry is going now is towards producing zero prototypes. So if you're going to achieve that goal, and many companies are out there saying we don't want to do any physical testing at all. If you're going to achieve that goal, then you need to increase the amount of simulation you're doing and different types of simulation. You need to start to look at variation. It needs to be more probabilistic, which will come on later. But this industry will push that goal. And the way it will push that goal is it will start to reduce the budget for doing physical testing. So we're going to have to do more and more simulation. But that is what this industry will achieve. Typical example here, this is around about 2012 from JLR. So even over a decade ago, this industry was getting a really good handle on making sure that we could start to correlate using them types of techniques. The real interesting thing now starts to be, well, if I can use these tools in simulation, can I use these tools in design? And then I met another inspirational character, the founder, CEO of Altair. Around about 2000, I started Altair in 1998. I met our CEO, Jim Scapper. Jim even then was talking about there will be an explosion in simulation. You know, we started to see these new architectures of HPC coming on board, cluster machines. We felt that this would really harness and really accelerate. And we started to use technologies like optimization started to come in. And optimization was really special from a design perspective because it started to give ideas of geometric layout. Geometry was always the designer always drove the geometry, and now all of a sudden clever technologies like topology optimization were starting to give the designer inspiration about where basically you could start to define optimum geometry. And this then started to accelerate. We're using lots of response surface methods. So yeah, and this journey still continues. this push and this noise around AI is also a massive pull-through for optimization technology as well. So again, this was only 2001. This is one of the really success stories. It's an aerospace example. This is Airbus A380 looking at a pack of ribs at the front of the plane. They went for the traditional orthogonal type of structure that they've ever done. Far too heavy. They needed to explore something a bit more radical, and we come up with this truss type structure. So every time now we are designing vehicles, we're using a lot of topology optimization to define the architectures. Now where are we? Well, I think increasingly what we're seeing is that now data is starting to come in. This is probably why we are here today. We've got lots of data now. And now we've got lots of data, then we can start exploring different techniques like machine learning. So this is really exciting again. This is complemented by the fact that the products that are being created, they're massively censored. So on a modern car, you've got at least 50 sensors, and growing. So you're pulling down loads and loads of data. So let's just look at this data from the point of view of simulation. So when I was at college, I learned if I want my model to agree with the physical artifact, then there's 4 areas that you need to basically focus on. Make sure that the geometry idealization is good, material characterization, the loading conditions, and the boundary conditions. So if your model wasn't agreeing, focus on the physics. Where am I different? Where is this discrepancy? And I think you can basically break it down to, looking at the body that you're modeling and looking at the environment. Now, what we basically see is we see variation in all of these. Have I idealized this correctly? When it goes through an industrialization process, it's not going to be the as-designed geometry. It's going to be different. Same with the material. Material will have a variation. It won't be this nominal value. It will have this variation. The design, these idealistic load cases that you've designed these structures for, maybe aren't the ones that you see out in the field, but all of a sudden you're getting this field data back and you start to get more insight into what's driving genuinely your design. And the same with the boundary conditions. So data will start producing insight to produce more refined design. And in a very simple way, then if you can look at, say, a coin toss, for example, there's actually PhDs on coin tossing. If you look back, you'll find 1 or 2 PhDs. Quite interesting. Some studies done whereby, I think 300 years ago, they invented a coin tossing machine, which made sure that the velocity imparted on the coin toss was consistent. But yeah, I don't want to go there too much. But so when you toss a coin, is that deterministic? Well, to my mind, it is deterministic. If I knew everything, if I make a call back to them 4 areas, then I should be able to determine whether it's heads or tails. If I have the right velocity imparted, the most crucial thing is the attitude of impact when it hits the surface, whether it's going to be a heads or a tail. So yes, it's deterministic, but in order to basically simplify that variability, then we can start using probabilistic assessments. And there's a nice, simple probabilistic distribution function of a coin toss, where if I throw 20 coin tosses, then that's my distribution. I'm going to get so much, I get 10 heads out of the 20, or now I've got 9, but yeah, so then I can start building them distributions into my simulation, powered by the data. And when I talked about that 0 prototype mission, then this is an important part of that. There you go. So let's have some real world examples just to show when I talked about these computational intelligence and how we're applying them to real world design. I've just chosen a selection. There's sort of many out there, but yeah, let me start. One thing which is basically growing great momentum is these meshless technologies. Altair's a great meshless technology, the leading one, I would say. I'm from Altair. It's called SimSolid, and this works directly on the CAD data. So now, if we know that something will directly work on the geometric data, and we're not going to spend weeks developing finite element models or CFD models, this is a game changer. And we can even put this in the hands of the designer as well as the engineer to basically have a quick structural assessment. So we spoke a lot about speed. You know, we can get our CAD data, just kindly permission from Jaguar Land Rover. We can directly do a strength assessment on it or a modal assessment on it. You know, we've got a significant reduction in man days. So these are the new technologies that are coming in, which will start to revolutionize the design process. This one is quite an older one. It's basically a really nice probabilistic assessment, which we mentioned before. We use response surface methods. We're using deterministic simulation, and we can run a Monte Carlo simulation on the response surface. I like this example because it's a great aid to looking at controllable and non-controllable design variables. So the setup for this is very similar to an optimization setup. It's just the concept of the design variables is completely different. It's you have something which is nominal, and you're looking to see what the probability distribution function is. So this is on a Mars lander concept. There was various conflicting load cases. This is a full explicit dynamic simulation. One was impacting rock, a certain inclined value. The other load case was a flat bottom drop. There was a trade-off. They were conflicting from an optimization point of view, but from a robustness point of view, we then started to look at some of the design variables. So even on Mars, we understand apparently what the PDFs are for the wind speed of that landing site, even the rock distribution. And then I think there's various parameters, again, that were associated with the craft itself, the angle and the pitch rate. So some of these in general are uncontrollable. We can't change the wind, obviously. Could change the landing site, but I'm not too sure it was worth it. But there are things that we can control within the structure. They may cost more to control. And again, one thing about these technologies is that we gain more engineering insight into the complex system itself. So this is a proper simulation. It's in a high visualization package that we put it in. But yeah, so that's a failure. Once it's rolled over and it hits on its all the landing gears destroyed, and so it's a real mess. So when we went back to the client and we told them, well, we've estimated and its probability of success around about 68%, we had a meltdown from the client. So this is great information from the client. I think the client always knew that this was high risk, but probably not that high. So then we locked down some of the other parameters, and we did more of a controlled. We controlled some of them design variables a bit more, and we started to get a higher success rate. So yeah, that's a really nice example. And I think now we will be seeing more of these type of probabilistic assessments, because if we're going to look at the variability, the only way to guarantee robustness of these products is basically using simulation. You cannot do all of this physically. It's just impossible. So I think the AI technology, coming from Altair, as I say, we're very familiar with the response surfaces, with GAs. So for us, the extension of using neural nets and wasn't a massive step, but I think we're all on that journey. I think the journey that we have is obviously there's two areas that the automotive industry is really focused on. They are two areas which are massively, massively complex. So I think it's like a journey that we need to go on in order to achieve the goal. And they are at computational fluid dynamics, which is massively expensive. And the other one is crash. So if we just look here, then we spoke a little bit about high performance computing and the importance of high performance computing. This is Altair's GPU accelerated CFD code, which is UltraFluidX. This was kindly given to us by Aston Martin. And again, you can see the massive reduction in computation that we can achieve through accelerated CFD using GPUs. And obviously, a lot of the AI architecture is around GPUs as well, so there's a commonality there. So I think when you look at AI, and particularly for external aerodynamics, you'll find papers published by Toyota, paper published by Volkswagen. I think here, I think it's all about trying to predict some of these contours and draw inference from these contours. So with optimization, we are very much constrained to maybe looking at a handful of nodes and having them as our response, or maybe elements. But here, now spatially, you're able to look at the complete picture in a transient way. So it starts to open up a lot more to almost be a reference for simulation. So as we all know, we start to train these. The training of these models is extremely expensive if you're looking at external aero. And external aero is once again, it's really complicated from the fact that it's not just the external shape. Now and again, if you look at the internals, there's a massive amount of internal ducting. And slight changes to these geometries can completely change the behavior. And the other complication is that in a car program, each generation of vehicle is different. It could have new targets, new input on designs. So you need that transfer learning. If you start building these models for one program, you need to make sure that you can utilize that on the next program. So transfer learning of these models is extremely important. So we're all upon this sort of journey. This is a typical example. This is looking at drag in this case, trying to predict drag throughout this vehicle, and then you come up with a summation of this. This is trained just on I think about 11 runs to train this, which is very undersampled. But it's starting to give some sort of direction, and these physics-informed neural nets, then, again, we can understand where we're getting these sort of discrepancies. I mean, for me, whoever did this, there's a massive discrepancy just from an offset. So you can start training and understanding where you have this sort of difference and start to improve these sort of models. But these are top of the range. There's smaller areas that we can focus on, like just looking at an airbag in isolation, an airbag test. We can basically do many simulations. It's a lot cheaper. These are very expensive. Even got accelerated GPU, they're still very expensive. Now, modern vehicle design. Let me move on to structures and present an example here. This, I know you're probably not that familiar with vehicle design, but this is just stunning. So, throughout the whole of my career, never seen anything like this before. It is stunning, and thank you to Jaguar Land Rover for helping us, to letting us go out in the public and use this. This is what modern vehicle design is about. This is what modern vehicle design will be in the future. It's using loads of optimization, and then it's starting to use AI in a real positive, impactful way. So I've really built this up now. I hope it's not an anticlimax, but it looks great anyway. So let me just start a little bit. So as I mentioned before, we always start with topology optimization, depending on whether it's a clean slate vehicle, or maybe it could have some carryover, or maybe there's certain areas they don't want us to touch. But in general, we're using topology optimization. So people who are not familiar with topology optimization, it deals in space, and then you can start to define where it's telling you need to put structure. So we now routinely in our office use this type of technology to tell us where we should basically put space. And then once we've got the more the general layout, and again, in order to do this topology optimization, we're putting in all the attribute load cases that we want to assess it for. It's an optimizer, so it's giving us the minimum mass. Then we're putting pseudo crash loads in because it's not a crash solver, but we have to put pseudo loads to be representative. And then, so more detailed definition of various architectures in here. We experiment a lot with different types of constraints, different types of packaging to give us some insight into what if we package the battery in a certain way, how then does that start to affect the global nature of this sort of structure. And then this is actually looking at various battery configurations, various support frame layouts, and then trying to understand what is the best way that the topology wants to connect these type of packaging battery pack to the rest of the structure. So once again, we're starting to take some more ownership of the geometry and the architecture. It's the speed as well that you can do these things. This is really impressive. Again, everything is about speed. And then what we start to come out with from there is these, what we call these lighter models. In some areas, we're just using boxes when we've not got the actual section geometry. But we've got these very light models, and we've done loads of work to make sure that these lighter, quick models give good agreement to very detailed, unwieldy, finite element models. So we're very comfortable using these lighter models. And then when you've got these lighter models, you can start exercising these models. There's very few companies that basically can take very detailed 3D finite element models and have the computing power to explore design spaces. What's happening in the automotive industry is them using high levels of models which they can't explore, they can't exercise. So these lighter models are just ideal to look at things like optimization and AI. So here you see in some areas we're having to put more detail in because the crash requires it. But it's this way that we can manipulate these models and have these lighter models. So now that we've got the lighter models, then we can start running them really quickly. We can start using optimization. So the optimization in this case is using OptiStrut. So we're optimizing for NVH performance, and in our crash code radios, we're starting to look at these crash load cases. Now these load cases, if you have a more detailed model, even with a reasonable amount of compute, they would take days. So they're prohibitive for any design exploration. But whereas these models, we can run and we can explore. So if we can run and explore, then that's what we can do really rapidly. you see here that there's various variations that we can start off with, and then we can do various optimization studies on them variations. So again, what we're doing is we're rapidly exploring this design space with optimization, looking at all these multi-variations. It's very rare in a car design that you're just designing a single vehicle. They're designing a platform, and from that platform you generate multi-variants from that platform. So your topology optimization and your strategies need to deal with these multi-models. I mentioned sort of side pole. So all of a sudden now we can run loads and loads of these. We can do optimization. We can start to vary various design variables within that crash for side pole, and start to get a feel of what does crash optimization actually look like. So before, one of the things with crash optimization, these design spaces are horrendously nonlinear. Yeah, I mean, really nonlinear. I mean, they've got singularities, they've got discontinuities, they're a nightmare. And now and again, you'd come up with an optimum, and you'd say to the crash engineer, "What do you think of this?" And the crash engineer would say, "No, I don't like it." I mean, what you don't like about it? No, this is not a robust crash system. It may be your optimum, but from a robustness point of view, this is not the system that I want. So there was always that nagging subjectivity that you're letting things being driven a lot by maybe individual crash engineers. But I think now with this AI, what we're starting to do is do classification. So AI really good at basically recognizing, is it a dog, is it a cat? Well, it can also say, yeah, this is a great crash system. This is the crash system that I want. So if you look at various types of crash behavior here, then there's a mixture of top face buckling, side buckling, buckling on both sides. You know, this isn't good. What I want no buckling, thank you very much. So now we can start building that constraint or that classification into our DOEs. So here you basically see blue and red, the cluster, it's cluster 3, which is the no buckling, the green, which is the one that we're really interested in. But when you're running this amount of crash results, everything needs to be automatic. The engineer can't be going in, and I mean, he might be able to spot check one or two, but he can't be going in. Everything must be automated. So then you can do a Porto front optimization, so you can start to get a feel for what the optimization space is actually looking at by doing a Porto front. So you can see here that some of the green isn't giving the best mass results. This is the best mass result that we've got here for the green. So why don't we try and relax that constraint? Why don't we try and just relax it a little bit, and then maybe rerun the Porto, so we then put this relaxation of the constraint into the optimizer, and then we see then that we're shifting further to your left, and we're getting better results with the behavior that we actually wanted. So this is the introduction. It's the start of AI basically starting to impact in a real positive way our design. So as I say, it's obviously for components, and there's a lot on physics AI, a lot more simpler. It's starting to have that impact. So I want to just briefly talk about digital twins, because it contains quite a lot of what we discussed here. So what is a digital twin? I mean, obviously it's a replicant of the physical artifact, and it tries to capture all the attributes of that physical artifact, or the attributes that need to be captured. I think it's really exciting, because what we see now is these smart products. So we're seeing a revolution that's been accelerated. What do I mean by smart products? Well, if you look at a modern EV, this is a smart product. It's becoming software defined, it's massively connected, stacked out with electronics, it's multi-physics. It's got a battery pack in there that's generating a thermoelectric response. It needs cooling. These are really sort of complex structures. So by way of introduction to digital twins, let me introduce you to the most complex product on the planet, which is yourselves. So there's great analogies, I think, between the human body and what I'm about to introduce, which is a battery pack. So if you look at the physical twin, it's got the body, which is mechanical, got a bit of CFD in there. It's got a control system, a very advanced control system, and it's got some good sensors. Sensors are not as good as they could be. I mean, if we had great sensors, then we wouldn't be having heart attacks. We need better sensors. So we need to improve there. The digital twin, it can be a multi-physics structure. It's a challenge, but yeah, we're getting the multi-physics structures. Control system, if you look at a modern day car, it's got at least 5 control systems now. So it's probably not as sophisticated as the brain, but it's got 5 control systems in at the moment and growing. And then censored, it's censored to death. I mean, it's got data flowing through its veins everywhere. So it can understand now what's going wrong. It's over-the-air data, it can send data back. So it's very, very sophisticated. So let's look at these sort of twins, because I've got an obsession with batteries and battery packs. So this is a little small tester demonstrator. There's 41 cells in this pack, and we just want to make sure that we can test the response of our tool OptiStrut to predict the thermoelectric response of this. So, I mean, I think this is a real key, because once again, going back to the performance, the industry wants to rapidly charge these things a lot quicker. And if it needs to do that, then it needs confidence to do that, that it's not going to produce a thermal runaway. So you can get, now and again, you can get the specification off the battery manufacturer, and it'll say, don't charge it beyond this limit, this speed. But we want to charge quicker than that. So how do we do that without risk? Well, we've got a cooling system. So essentially, we can control the cooling so that we don't introduce aging effects into this sort of battery. So it's a great optimization problem, which I'm not going into, but essentially you want to suck heat out of the battery. If you suck heat out too much, then your delta T is going to be too great, and your delta T will kill the performance of the battery. So it's a great optimization problem, but I won't go into that, not in this talk. So here's your physical twin. It's having a rapid charge push through it, and that's our digital twin. So we're getting, I don't think we go into the correlation here, but again, it's testing really well. We're really confident. So that's it on the digital twin side, and I think that will continue. So for the future vision, the way I see it is like this. It's all the elements that we've discussed converging together, which is probably the title of your conference, your modeling, your data, and your AI. These things will all start to merge together. So I put a battery pack here. That's a typical battery pack. Nearly, I think there's probably about 6,000 cylindrical cells in these packs, but that's not the point. I think what you're on is this sort of journey where basically you can imagine when the product is actually born, then it's gone through this industrialization process. That industrialization process has introduced genuine noise into that through its assembly process. It's been assembled, it's been bolted, spot welded, stamped. It's going to not be perfect, but the increase of data and the way it's monitoring, then you're going to start producing a unique twin of that as it's born, as it comes out of the plant. You'll have that unique twin. So now when it leaves the plant, then like humans, we've got different operation modes. So different service cycles. Some may sleep a lot, some may not sleep too much. Or from a drive point of view, we all have different drive styles. Now we're monitoring the drive styles. We know now, basically from a predictive maintenance, some people are driving these structures more than others. We can start tailoring the battery management system to that driving style. So this is about modern development. So essentially, each one of these physical items will have a corresponding unique digital twin, and that through data, through over-the-air data, coming back through us then doing a cause and effect, looking at our digital twin, all feeding into some central system. Now, this at the moment is a vision, but it's not too far away. So we're really driving towards this. We have all the pieces to assemble this. So this is coming together probably quicker than what you think. Very, very exciting, huh? This is genuine convergence between them three areas. That's what I think the future will be. And then obviously to complement that, I go back to my comments about, we need more and more computing. I mean, obviously we have lots of discussions about quantum. How far is quantum away? And some say we'll have quantum in 10 years. But quantum again, maybe I won't have to say I still haven't got enough compute. I don't know. But I love this. This is from a BBC program called Devs. And that was talking about a complete virtual world that was created via quantum. And this is their view of a quantum machine, which is really beautiful, actually. It's a really nice creation. So if you've got time, it's even on the iPlayer. It's a program called Devs. Go and see it. It's about creating a virtual reality. So that's it. And I think what is really fascinating is that if you look at, that's Google's quantum computer. There's quite a few quantum computers. I've actually seen one in the UK at Oxford Quantum Circuits. So yeah, maybe that's the solution to my problem on wanting more compute. So I think computational intelligence, is the key to product development speed. I think industry is adopting it more aggressively. It's not adopting it quick enough, and I think if it really wants to go quicker, then I think we're giving it the answer. So that's my email address, and if anybody wants to collaborate, then we're open to collaboration. Altair is a very open company. And then finally, the picture of my old professor, and I think he'd be really proud of where we are now with his vision of the real virtual reality. I often think about what would he say, and I think I know what he'd say probably what took you so long, probably. Okay, so that's me through. Hopefully that was of interest. Thank you.
Thank you. It was a very inspirational talk. I have some suggestions of what you can put in 2030.
Thank you. I don't think I'll be around in 2030, so maybe my predecessor.
Suggestions here. So, for example, you mentioned quantum computing, but in between what we have now and quantum, we're going to have neuromorphic neuromorphic is emerging. For example, in the UK, EPSRC is defining as a strategy over the next 5 years to invest in neuromorphic hardware. These are hardware that behaves like brain functions and so on. We are already seeing them emerging. They solve a very big problem related with temperature because they are massively parallel but more flexible than.
I think I'd like to follow up on that. I mean, just for your reference, I don't know whether you know Riverlane in the UK. They basically develop the operating system for quantum. Altair is an investor in Riverlane.
In terms of computational intelligence, I'm going to say that we are now moving towards computational cognition, systems that learn how to learn, basically, from the context. Imagine that you can ask the material, what do you think about this new design? And we are moving towards that. Simulation, we are moving towards co-design with cognitive edge devices. So imagine that you have your vehicle, you sell your vehicle to the customer, and the vehicle then starts to learn with the customer and how to optimize the main aspects. And finally, the transfer learning is going to be converted into federative learning. All of these devices then will be feeding up into your digital twin and this cooperation. So that was my point.
Thank you.
Thank you. Second question here.
I'm curious about the optimization problem, like optimizing the shape of a car. Do you consider the cost of manufacturing during the optimization process?
No, I think that, I mean, obviously there's such a relationship with weight, and I think a lot of the cost relating to the build, the manufacturing process, it's already been covered by the OEM, so we very rarely get that piece. It's a good observation that, you know, I had them three, I had the mass, performance and cost, but it's very rare that we actually get the cost, and our focus is on that mass. And now and again we deal with body and white directors, and they will kill for grams if you can get it out of that body and white. They have such a focus on mass. So no, we don't. But we can put, obviously we can put any optimization function we have, but
Can be considered as a factor during the optimization?
yeah, you can put it in. You can put it in. I think the thing we also find with cost is that there's then debate about, you know, what is the right cost, and so you have to play around with it a little bit, but it's a good observation. We don't, our focus normally is just on mass because there's such a dependency on mass.
Following that point, you know, in terms of cost, but I have a different story. I'm not doing any computational modeling. We are basically just in the chemical engineering industry and using the kind of tools to do simulation. But I'm just following up with that question in terms of cost. What do you think of safety, especially when now people just when you do a design using a computer, you know, for modeling, especially now people are using EV, right? And then the question is how and where we should put the battery. How to make sure the battery not going to cause any fire and not going to cause any problem. So take that into account.
Yeah. So we have, I mean, once again, it's such a rapidly changing area. I mentioned that before about battery technologies and things like this. So if you look at lithium, then obviously lithium can be unstable. So we basically have certain deflection limits, so that things like side pole, for instance, that will not intrude into that battery pack. So we are protecting it, if you like, indirectly from impact. But you know, there's new chemistries that basically are out. There's LFP, which is supposed to be a lot more stable, and that's the road that Volkswagen are going down. It hasn't got the energy density, but it is more stable. It is it costs less, and then there's this holy grail of solid state, which again would be more stable. And now and again, we have Nissan and we have Toyota saying that they will have vehicles running in 2027, 2028 with solid state. But I think there's still some skepticism, and maybe that is not going to happen. Or if it is, it's just like a couple of demonstrator vehicles, and really maybe solid state is more like a 2030 technology.
That's very interesting talk, thank you. I was curious, it seems like for the battery, the visual thing, you have the idea is you have real-time feedback to update you, but I was wondering if you're trying to move towards a purely digital, no prototype, then your time horizon gets so long where you're trying to predict, say, how this car performs for 200,000 miles. Do you think that error accumulation, whether it's AI or the model, the error propagation, how would you overcome that over such a long time horizon without the real world feedback?
I think that's a great point. So, I mean, the whole thing about real time, as an engineer, then a lot of the calculations that we're doing here, it basically looking at the physical understanding of the actual system, and they're not in real time. And that isn't a disadvantage for a lot of the studies that we're doing, because we haven't got hardware in the loop or software in the loop. But I think like for crash, for instance, you wouldn't want that in real time, because that's a millisecond event. But I don't think yet we've basically got to a reduced order model, a cheap surrogate model that will truly reflect what's happening in that pack yet. We've not really trained it yet. And I think that's one of the missing pieces, is to get confidence that whatever we come up with for that reduced order model will actually capture all of that physics. So again, I think when I presented that vision, it is a vision, and that's where we have to march to. Because the thing with the battery pack, just getting into the physics again, you can't create just a reduced order model of the battery itself. It's such a coupled system. Everything within that battery pack is temperature dependent, and now and again you're getting cooling from the plate. You're getting heating from the bus bars. It's so complicated. So we've not really got to the point yet where we're going to produce that reduced order model. But when we do, I think the tying back to the over-the-air data, I think that would be key. But that will be a challenge, because I'm not too sure exactly what we can measure other than when we start to get some issues. But yeah, again, we have to build in the noise. Yeah. So I was told that nearly 40% of the amount of warranty claims that are due to the pack is massive, because of the noise in that manufacture. Little fuse wires, or the way that they're located. I mean, that's why doing these robustness studies, we need to get stuck into that and really understand more about what's driving these systems. So yeah, I think you're ahead of us on that one. We're not there yet.
In the same context, what you presented is a digital twin for every battery, right? So you have a digital twin that's updated from the data of every battery. So you have individual digital twins for every single battery pack that you have. And the more data you get, the closer you get to the actual battery pack. You could see every battery pack as deviation from the ideal battery pack, but because of noise or manufacturing issues or whatsoever, which in essence is your digital copy, like the model, like the physics-based model. At what point do we get rid of the physics-based model because we have enough data? Have you thought about how much we separate or we create spaces for the physics-based model versus the AI?
Yeah, I think we're along that journey. I think for us it needs to start with us really understanding the manufacturing variability and that variation inside that sort of battery pack, which is a major challenge with the way that these things are constructed together. And I think we need to start there. And then, if you've got issues and you get over-the-air data back, then I think you can then use that model to explore whether there's a consistency between what you can predict in the virtual against what you're seeing in the physical. So an example of that is, say a fuse wire has gone somewhere and you're getting a response back, then you need to try and disconnect a few fuse wires to see whether that correlates with what you're seeing with the over-the-air data. And I think that's the journey that all these companies are on. But I don't think, it was a vision. I don't think anybody's really pieced all that together. But hopefully what I presented shows you that all the pieces are there. And I think companies will drive to that really quickly. Because ultimately what it represents is complete elimination of warranty. Now, if you ask any company, what is its biggest barrier to earning more profit, it's warranty. Warranty of any car company, you can look at any of their reports, it's around about 10% of their turnover. It's massive. So if you can say to them, I think I can eliminate your warranty, or at least some of the issues we're talking about here, you know, they should be all over it. Huh? The only way they will eliminate warranty is by understanding this variation. And you're not going to understand this variation by accident. You're going to have to do the hard work of going to the plant, measuring constantly to understand that variation, and using these types of simulation models then to really explore the interaction of that variation. That's what I feel.
Thank you, Royston. Do we have more questions? Okay, 2 more, and then it's time for first.
You show the value of data, but is there a point, there's some discussion on who owns the data, and do you have to pay for that? What legislation varies for that?
Yeah, I think it's an absolute nightmare. I think the ownership is a nightmare, and it's a barrier. A lot of it can be a barrier to doing what we want to do, because there's a number of software companies that basically, you know, they have a software product, they're storing the data. Even for the client, they're storing the data, and they want to own the data. So everybody's after owning data. And not sharing it. Everybody wants to monetize that data, and that can be a barrier to some of the things that we want to do. So getting manufacturing data, it's a nightmare.
So the owner of the cars generating the data,
You think you
that data, or is the car manufacturing owning that data?
I know about the plants. I know about the plants that at times you'd expect the OEM to own that data, but he doesn't own that data, and we have problems getting hold of that data. I mean, the only thing I've got is that anecdotal of over-the-air data going to Tesla. So Tesla have that data, and they're using that data. I think most of them now are using that over-the-air data. Hopefully there's loads of privacy around that data. We hear when that privacy's been broken, obviously, but you know, they're using that data to refine their designs, to refine the battery management system and things like this. So that over-the-air data, again, when I was talking about refining what sort of duty cycles a drive is genuinely using, then the vision then is to customize every battery management system for that particular driver.
Okay, final question.
Yeah, thank you for a very show of pace of impressive work. And I was just curious, since you mentioned the mass and the cost and the performance, and we have these typical sort of objectives we try to achieve. And now with the age of more computational power and the AI and all that, have you already considered, or do you have it in your vision to have novelty as one objective, so that you could say, hand over like, okay, this is an old design, this is old design in the case of geometry, for example. And you still have that feasibility constraint. Obviously it needs to be safe and do what you're doing right now. But then now you're sort of looking around, from my perspective, sort of maybe, I'm not familiar with the field, but sort of local optimist, but sort of exploring more, showing like it can still be an acceptable solution if it's close to the old design, but it gets more points if it's something more novel. So have you considered that yet, or what's your? I think
indirect. It's interesting that the talk is about speed, which indirectly is about productivity. But productivity for a lot of the car companies is boring. What it really wants is innovation. So you see in our message, we've got innovation, and the computational intelligence is generating innovation. And what that innovation hopefully will do, it will generate ideas which the designer or the engineer hasn't thought about. And I guess in its most purest form of that, I'd say the topology is a good example whereby it's dealing in space and then it's trying to come up with the optimum layout within that space. I think again, you know, there's probably more scope for stronger examples. The more flexibility, the more freedom that you can give the optimizer, then it'll come up with something that maybe the designer hasn't thought of, something counterintuitive. We've done that in the past with, say, knee bolsters, for instance, which is like a crash bracket. And there we used a load of harmonic shape functions, and we just threw them all in, and then it come up with this double system, which is really neat. And that could actually be made because it was extruded. So, but you're right. I mean, the more innovation really is key. But when you speak to a body and white engineer, he doesn't care about innovation. That's too fluffy for him. All he wants to do is hit his mass and his performance targets within that duration, and then he's done. Innovation is something that somebody else can care about, but yeah, that's his focus. But yeah, innovation is the real executive player, huh? Which is why AI has got such a hold at the moment.
Thank you, Royston.
Yeah.
So we are not going to take any more questions. Royston will be with us for lunch. If you can grab him, by all means try. I suppose one of the main takeaway message from Royston's talk is Royston from industry and taking a senior leadership role at a major company, multinational business. I suppose this is a clear message to us, or many of us who works in that world. This dream, we say, of this initiative or objective, by putting together, traditionally we got modeling, we got data in the engineering space, very successful, draw proof its value. Now, what AI means in this engineering scope. Clearly, it's happening, industry is jumping onto that, and we don't want to be dragging the feet, right? We should be leading that and contribute to the innovation. I hope that will be a useful message for all of us to think about. Thank you, everyone, and thank you.